I think we need to get started. I'm the co-chair of the CESM Paleoclimate Working Group, and I want to thank you everyone for joining the meeting. And as you can see here, we have a new external co-chair from Brown University, Junyun Li. Unfortunately, she cannot be with us today, so I will be chairing the first session, and Sophia will help us chairing the second session. I also want to take this opportunity to thank our previous external co-chairs, Samantha and Ran, for their contribution over many, many years. Okay, next slide. We have a list of very interesting talks, so some logistics. Each talk will have 15 minutes, including a Q&A session at the end. We will give you a reminder when there's 2 minutes left, so you want to wrap up and take a few questions after that. We will have a break at around 2:30. And the session need to be conclude at 4 p.m. for the CESM plenary wrap-up. So we want to stay on time for that. And if you have questions, if in the room, you can walk to the microphone in the middle of the room. And if you are watching online, we are using Slido for online questions. So you go to slido.com and use CESM. I think we are now in the room south, and you can also find the Slido link in the email. We are using the south for our Slido, handling our Slido questions. And just a reminder here, if you want to, the easiest way to access working group resources is our website. We actively working on maintaining and updating the website. Over there, you can see a lot of interesting and new simulations and some other information as well. If you're not on our email list, please consider subscribing to our email list. And one more update about the CESM3 LGM. So here I'm updating the recipe for setting up CESM3 LGM. If you are working on paleo simulation using CESM3, if you want to know how to do that for, say, another time period, this would be a useful resources. My goal for the CESM3 LGM is to, in the future, to create a comp set so everyone can run CESM3 LGM. I think this is important because you can see that there are a lot of ongoing machine learning and hybrid model-based work. And if you want to test your emulator or hybrid model and under this LGM out-of-sample condition, this will be very easy to do in the future with a comp set. You can create an LGM and hopefully test your hybrid model, say. And we are also working on other time periods as well. Please talk to us if you are interested and if you want to learn more. One more highlight, I want to show this again. You have already seen this slide from Dave's talk. So we are co-leading the development of isotopes in CESM3. And it will be used the modernized code structure. So hopefully from now on, the isotope code will stay in the main branch of CESM. And I want to say that this is from the communication with the community multiple times. So every time we try to seek input from the community, isotopes is on the top of the list. So we are really, really happy that we find the funding resources to do this this time. And finally, we will have an informal happy hour after the session, the entire session. So at around 5:15. So some of us, we have a car here, so we can carpool together. Otherwise, you can take an Uber as a group, as fine. That's also fine. And everyone is welcome. With that, I will stop here. We don't have time for questions. Just talk to me afterwards if you have any questions. So we will switch to our first talk. Our first talk is from Nicole Cosentino.
Yes.
Looks
Hi, Jan, do you see my screen?
Yes.
Okay. So thank you very much for inviting me to this session. I am a researcher based in Buenos Aires. And today I'd like to share with you results from a study that was published recently, looking for relationships between volcanism in the Andes and late Miocene cooling. So we know that mineral dust aerosols and volcanic ash aerosols, they have the potential to fertilize the oceans, and in doing so, to reduce atmospheric CO2 concentrations. Specifically for mineral dust aerosols, the consensus is that this has a cooling effect on climate, although the uncertainty is quite high. For volcanic ash aerosols, the effect might be similar, and there's also many uncertainties, including the deposition rate of volcanic ash aerosols in the ocean, grain size distribution at deposition, the chemical composition of the ash, and the potential for the presence of micronutrients, how bioaccessible these nutrients are, and of course, the ecosystem of the surface ocean that will also control these effects, among other uncertainties. So the hypothesis for this study is that late Miocene Central Andean volcanism contributed to global late Miocene cooling by fertilizing the Southern Ocean. And so one of the observations is a compilation of magmatic ages. We see that for the Central Andes, specifically for the Altiplano Puna volcanic complex, there's a rise in activity beginning at 10 million years and peaking at 7 million years. This APVC region is the largest active silicic magma system on Earth, which is highly explosive. And we see both for mid-latitude northern and southern hemisphere that there's been a cooling trend on SST records based on alkanon records and oxidation isotopes from benthic foraminifera. So there's also some other geochemical and paleontological evidence that points to a possible connection between magmatism in Central Andes and the late Miocene cooling. First of all, we have atmospheric CO2 that decreases between 8.5 and 6.2 million years. And delta carbon-13 in benthic foraminifera falls quite a lot, between 7.5 and 6.2. This is the so-called late Miocene carbon isotope shift, the LMCIS. And this has been associated to increased ocean fertilization and productivity. And finally, there's a sharp increase in deep ocean phosphate concentrations, and also in diatom occurrences between 7 and 6 million years, based on marine core records, which all point to heightened productivity. So all these observations are consistent with a link between Central Andes volcanic fertilization and late Miocene cooling at million-year scale. But we would like to test this based on simulations. So we carry out a modeling strategy based on 3 steps. The first step is to simulate the particle life cycle of ash aerosols with high split. So we first geologically reconstructed a long-term mean late Miocene ash emission rate based on volcanic deposits close to the source. And then we used present-day meteorological data to represent atmospheric advection and diffusion. And finally, we turn on dry and wet particle deposition. The next step was to use CESM to represent the carbon cycle at short-term, seasonal to centennial timescales. We used a fully coupled CESM with CAM4 and at low resolution, with the ocean biogeochemistry module MARBLE activated. And we represented the co-limitation of primary productivity based on three nutrients, phosphorus, iron, and silicon. So we first ran a control simulation for 1,300 years with pre-industrial climate, with dust aerosols, but with no ash aerosols. So after the control, we applied 4 ash-derived nutrient pulses every 75 years. And it must be said that these simulations were run with a fixed atmospheric CO2 and no radiative climate feedback from ash aerosols. And finally, we performed CG1, which is an intermediate complexity Earth system model, millennial scale simulations of the carbon cycle. And in this case, the ocean biogeochemistry, the limitation in the ocean was represented based on iron and phosphorus co-limitation. And we performed 5 experiments to test the influence of volcanic eruption frequency and magnitude and of dust on the ocean ecosystem. And so these are the results from the high-speed simulations for the present-day climate. And we see that mostly volcanic ash aerosols emitted from the central Andes mostly go into the South Atlantic and South Indian Oceans. And based on these ash flags, deposition ash flags, we derived nutrient deposition fluxes based on these ash deposition flags, but also based on the content of different micronutrients in close to source ash samples, and also how soluble these nutrients are, which is going to control how bioavailable the nutrients are to the primary producers. And so these are the results for the seasonal to centennial simulations based on CESM. Here I show results for the control simulation with ash aerosols, but without, with dust aerosols, but without volcanic ash aerosols. And this is showing a climatology for the austral summer on the left of chlorophyll concentration, and on the right on air to sea CO2 flux. And we see that dust aerosols produce a flux of CO2 into the ocean at seasonal scales. But then we apply the ash aerosol fluxes into the ocean, and we see increased CO2 fluxes into the ocean and chlorophyll A. What I show here on the right is a cumulative anomaly that is with respect to the non-ash control simulation of the total integrated in time fluxes of different variables. So the 3 vertical lines here in dashed lines represent the moment in time when we apply an ash input of nutrients, ash-derived nutrient inputs, along with time 0. And we see a stepwise increase in surface CO2 flux into the ocean with each input of ashes, alongside a stepwise increase in the particulate organic carbon flux at 100 meters below the surface of the ocean. And interestingly, we see a change in the ecosystem where diatoms are rising in productivity based on the biogenic flux at 100 meters below the surface of the ocean. the particulate organic carbon will go all the way to the seafloor, and an even smaller fraction of that will get buried in the sediments. And finally, these are the results for the CG1 millennial scale Earth system simulations. Here I show the simulated change in POC export flux and RC CO2 flux. And these time series here are showing for the first 500 years of the CG1 simulations. These are the panels on the left, and the results for the from 500 years to 20,000 years. These are the panels to the right. And on top here we see for the 5 different experiments we run on CG1, we have the experiment where we run an ash pulse every 75 years in black. Also, the experiment where we run this same periodicity in the ash inputs plus dust. And then in blue, we do an experiment where we raise the periodicity of the pulses of ash 3 times. And finally, in orange here, the experiment where we apply the 75-year cycle to the ash pulses, but with 12 times higher amounts. And basically, what we see here is that the experiment where we have a more frequent input of ashes produces a higher reduction in atmospheric CO2 long term. And also the addition of dust also helps to raise the delta PCO2. So some of the conclusions are that volcanism was particularly vigorous in the Central Andes during the late Miocene, with the APVC, the Altiplano Puna volcanic complex, which is the largest active silicic magma system on Earth. The late Miocene coincided with a period of major biogeochemical and climatic reorganizations, including late Miocene cooling, the late Miocene carbon isotope shift, and the late Miocene biogenic bloom. And our results suggest that more frequent ash pulses, potentially amplified by increased non-volcanic dust supply, can cause enhanced CO2 uptake in the Southern Ocean and lower atmospheric PCO2 by 15 ppm over 20,000 years. This is a small number, but it could be indicative that this process is contributing to cooler global conditions when combined with other processes that we have not represented in the model. So the limitations of the study is that there's a high uncertainty on the ash emission rates, grain size, periodicity of emissions, and plume injection height, which is going to control the distribution of ash aerosols. Also, we used present-day and pre-industrial climates, not late Miocene. And the total element concentrations and solubilities are also highly uncertain. And finally, I would like to share a more speculative hypothesis, which is whether late Miocene Central Andean volcanism could have triggered whale gigantism. And this is based on
2 minutes left.
Yeah, this is based on the total length of fossil whales that shows a rise during the late Miocene cooling, coinciding with Andean volcanism. This, however, is highly speculative so far. The connection would be that the increase in size could reflect the loss of productive shallow water habitats, the rise in productivity in the distant Southern Ocean, and the advantage of larger bodies for long-distance migrations. So finally, this is the paper where we show the results, and you can check more details here. And please, I'm open to questions if you have any. Thank you very much.
Thank you, Nico. Great work. Any questions?
Thank you.
Maybe I can ask one. Could you speculate if you run similar simulation, say with a Miocene boundary condition, should we expect a bigger CO2 response?
What we tested is the distribution of, what we did was to run the high-speed simulations to know where the ash aerosols are deposited in the ocean. And we did that for 10 years for different months of the year. And for the present day climate, we do not see a big change with seasons or intra-annual. So that stability in the present day climate could be indicative that maybe there's not so many changes with climate. So we will expect the distribution of ash aerosols to be similar in the late Miocene. But with respect to the CO2 response, that will really depend on the structure of the ecosystem, ocean ecosystem, and I do not really have an answer for that right now.
Thank you. In the interest of time, let's move on to our second talk. It's also from online. Our second talk is from Chunyu Yang.
Hi. Can you see me and hear the voice and the screen?
Yeah, this looks good.
Okay. Hi everyone. I'm Chunyu, a PhD student from the University of Connecticut, and today I'd like to share our ongoing work on how effective radiative forcing is amplified under Eocene sea surface temperatures and boundary conditions. Compared with the pre-industrial climate, the Eocene was substantially warmer, especially at high latitudes where sea ice was greatly reduced. This makes the Eocene an ideal test case for understanding how CO2 influences climate in a much warmer world. In a simple energy balance framework, the temperature response to CO2 depends on two factors: the radiative forcing itself and the climate feedback that follow. Previous Eocene studies have focused on the feedback set of this framework, particularly cloud feedbacks as a possible explanation for the high climate sensitivity inferred for the Eocene. And here we focus on the other side of the same framework, the forcing. At first glance, we often think of CO2 forcing as depending mainly on the change in CO2 concentration following this relationship. If that were true, doubling CO2 would produce the same forcing regardless of the background climate. However, recent studies suggest that this may not be the case. On the left, the same CO2 perturbation produces a larger IRF at the climate warms. And on the right, URF shows similar behavior across different CO2 backgrounds. Together, this study suggests that CO2 forcing itself may depend on the background climate state. So this naturally leads to the question we ask here, does CO2 forcing depend on the Eocene climate state? So to address this question, we ran 4 sets of fixed SST experiments. We combined 2 SST backgrounds using pre-industrial with 2 sets of boundary conditions using pre-industrial. The 2 matched cases are shown on the left and the 2 crossed cases are shown on the right. By comparing these 4 cases, we can separate the effects of SST, sea surface temperatures, and boundary conditions on CO2 forcing. For each case, we ran simulations from 1 times to 12 times pre-industrial CO2. Here are the main ERF results. Across our 4 experiment groups, ERF increases almost linearly with log CO2, but the slope depends on the background climate state. And here, apparently, the Eocene cases show systematically larger slopes than the pre-industrial cases. I also put published pre-industrial fixed SST ERF values on the plot as references. These references points fall close to our pre-industrial background fitted curve. And on the right, the regression analysis shows that the difference in slope are statistically significant among the 4 cases. So we were wondering what controls this slope. To think about that, we look back at some papers that explain why CO2 forcing is approximately logarithm in concentration. The first one here in 2014, they provide a simple column view. As CO2 increases, the effective emission level moves upward. Since higher levels are colder, less infrared radiation escapes to space, producing a radiative forcing. Because each CO2 doubling causes a similar upward shift of the emission level, the forcing scales approximately with log CO2. And then in 2022, ROMs make this picture more specific for CO2. They introduce the emission pressure, this PEM, which is the pressure level where radiation escapes to space. In the figure, each black dot represents a group of wave numbers in the 15 micron CO2 band. When CO2 doubles, this whole train shifts upward by across the same amount on the log pressure emission axis. And one group of wave numbers that used to emit from the warm surface now emits from the colder upper atmosphere. And each doubling moves about the same size group, so each doubling gives about the same forcing. That is the physical reason CO2 forcing is approximately proportional to log CO2. But Rome's explanation relies on the assumption that CO2 has a broad absorption band near 15 microns. And years later, Woodworth explained why this broad band exists, providing a quantum mechanical explanation for this K assumption underlying the Rome's framework. So after going through these Y-log papers, we found that temperature structure keeps appearing in the final expression for CO2 forcing. So we tried to bring lapse rate into the framework and see whether it can help us interpret the different slopes. This motivated us to look directly at the vertical temperature structure in our experiments. The first thing we noticed is that the temperature profiles nearly converge around this 54.6 hectopascal. Below this level, the profiles separate mainly by sea surface temperature states, while above it, they vary more with CO2 concentration. To better understand this feature, we next examine the zonal mean temperature differences. Here I only show 4 representative cases since the remaining simulations show very similar pattern. The top row isolates the sea surface temperature effect, while the bottom row isolates the boundary condition effect. The main result is that the sea surface temperature is much larger. It produces substantial warming throughout the lower and middle troposphere, whereas the boundary condition effect is weaker and more spatially variable. Importantly, these patterns are very similar at both this 1 times CO2 and 12 times CO2, suggests that the background climate state established a relative stable difference in vertical temperature structure. And another interesting thing is that this 54.6 level, here it stays close to the upper boundary of the strong sea surface temperature induced warming. And this same level also marks a transition in the boundary condition response where the sign and spatial structure began to change. Because this behavior appears consistently across CO2 concentration, so we wondered whether this level might be relevant to the ERF slope difference. To test this idea, we define gamma using the temperature difference between the surface and this 54.6 hectopascal, following the simplified framework proposed by Roms. We then multiplied log CO2 by the corresponding gamma for each experiment. And remarkably, once this scaling is applied, the 4 experiment groups nearly collapse onto the same line. And the slope differences that were significant before are no longer statistically distinguishable. So this suggests that the differences in vertical temperature structure account for most of the state dependency in the ERF response. And we wouldn't say this 54.6 is a hard physical boundary. This result probably depends quite a bit on how gamma is defined. And here I am following Rome's simplified definition. But for our simulations, this level turns out to be a useful diagnostic level. The temperature profile is nearly midday, and it lies in the lower stratosphere between the sea surface temperature controlled troposphere and the more radiatively controlled upper atmosphere. And using this gamma from this level also helps collapse the slopes. And so for now, this is as far as we take the gamma analysis. Gamma appears to explain much of the state dependency in ERF. We also wanted to understand the role of rapid adjustments. So we look at the rapid adjustments and how they contribute to the ERF differences. We use these radiative kernels to decompose the rapid adjustments. This method has two main parts. For the non-cloud adjustments, we apply the kernel to the simulated changes in temperature, water vapor, and surface albedo to estimate their radiative impacts. And for the cloud adjustments, the calculation is a bit more complicated. We start from the cloud radiative effect, and then apply corrections for this cloud masking and this forcing differences before separating the cloud response into long wave and short wave components. Most of these terms are straightforward to calculate. The main challenge is the forcing correction term because it can be comparable in magnitude to the cloud adjustment itself. So as a result, the diagnosed cloud adjustment is quite sensitive to the accuracy of the forcing estimate. Ideally, we would like to use instantaneous reinforcing for this correction. However, because we are still working through the port validation issue, so the kernel-based cloud adjustment analysis is not yet complete. But we still can take a look at the non-cloud results. Across the different kernels, the result is very consistent. The non-cloud adjustment is always negative, and as CO2 goes up, it gets more negative. The spread between kernels give us a sense of the kernel uncertainty, but the overall pattern is robust. This behavior is going in the opposite direction from the ERF, so it cannot be what drives the larger positive ERF. If anything, it acts to reduce or offset the ERF. So we still want to know how the cloud looks like. So although the kernel-based cloud adjustment is not finalized yet, we can still use this approximate partial radiative perturbation, aka APRP, to estimate the shortwave cloud contribution. This term is positive across all cases and generally grows with CO2. So it goes in the same direction as the ERF. That suggests shortwave clock change may be one contributor to the positive ERF differences. However, this magnitude of this shortwave cloud contribution is relatively small. So to see what remains unexplained, I calculate residual. The residual is that the total ERF minus the non-cloud adjustment from kernels and minus APRP shortwave cloud contribution. And the residual is still very large. So the terms we have so far does not close the ERF budget. And the residual is probably includes several things, but the long wave cloud part is likely a key one. So it is important for us to fix the forcing issue and get the kernel-based cloud adjustment, especially the long wave cloud result.
2 minutes left.
The last slide, the last slide summarizes the key findings so far. So we have one remaining challenge is the CM port validation. At the moment, the all-sky validation still does not pass. So if anyone has experience with CM5 port or insights into the all-sky validation issue, we will really appreciate your advice. That's all I have today. Thank you for your time.
Thank you, Chunyu. Great job. Any questions? Maybe I can ask one. What's your interpretation of the residual term? Have you considered specifically the stratospheric temperature? Will that somehow, after you considering that, will that close the budget better?
I don't know. I need to fix the kernel first.
Okay. Any questions from the audience? How about online? No. Okay, thank you again, Chunyu. We will move on to our third talk from Xiaojing Zhu.
Today, I will be talking about biogeochemical effects in ocean alkalinity enhancement and how we investigate them using two global ocean biogeochemical model configurations, MOM6 model and MOM6 global. This work is a collaborative effort involving
Thanks for staying for the last day afternoon session, and thanks John and Jun for convening the wonderful paleo working group session. It's my honor to be here today to introduce my work on the optical scale hydroclimate dipole in South America and discuss the impact from both remote tropical teleconnection and local forcing. Okay, why we care about the tropical South America? It is one of the largest deep convection center over the tropics. As we can see from the figure here shows the long wave radiation. And also the tropical South America support some of the largest biodiversity. The tropical South America provide the source and moisture for global climate system, and a better understanding of the hydroclimate change in this region can help us better understanding the global hydrological cycle. The precipitation in tropical South America is impacted by ITCZ, the South American summer monsoon, and also the South Atlantic convergence zone. In the core region of the South American summer monsoon, the precipitation saw very strong seasonal cycle. So most of the precipitation occurred during the monsoon mature season, the DJF. The moisture from the tropical Atlantic is delivered into the Amazon and blocked by the Andes, and channel the moisture toward the southeast of Brazil, and the intense supply of moisture induce intense convection over the western Amazon and also the tropical Andes, and that help establish the Bolivia high and also the northeast low. And we can see there is strong convection over the western Amazon and also the tropical Andes, and there is a relatively greatly substance over the northeast Brazil. So this east-west dipole pattern has also been reported from other timescales, like millennial and opto timescales, but the underlying mechanism is still under debated. Okay, so the opto scale, the east-west dipole pattern over the tropical American has been reported since 2009 based on the split awesome records showing anti-phase over the, northeast Brazil, and those from the rest of the tropical South America, including the western Amazon and also the southern Brazil. We can see over the northeast Brazil, there is more enriched Delta 18 precipitation during LGM relative to the early Holocene, but in the southern Brazil and the western Amazon, we see the opposite trend. So this has been contributed to the strength of the South American summer monsoon related to change in the local summer insolation. But with more available proxy records and longer records, the structure of this dipole pattern, as well as the underlying dynamic mechanism and the primary forcing, has been under debated. For example, there's a record from the Amazon lowlands, which shows it's a longer record, but it doesn't closely follow change in the optical forcing. It actually follows a CO2 level in the atmosphere. So this indicates maybe CO2 concentration also play a role here. And also, more attention has been concentrated on the South American summer monsoon, the local forcing, but it could also be impacted by remote forcing through oceanic and atmospheric teleconnection, and that has received much less attention on paleoclimate study. And also, we know the impact of isotope composition beyond the amount effect could also complicate the implication of water isotope proxy records. Okay, in this work, we're going to answer the following questions. What is the dominant external forcing driving the optical scale east-west dipole during the last deglaciation? And how do local and remote forcing influence the precipitation pattern? And what is the key physical processes controlling the spatial pattern of the delta 18 precipitation? Okay, to answer this question, we put together published water isotope-based proxy records spanning the last deglaciation, covering the tropical South America, including split awesome delta 18, leaf wax delta D, and S-core record. And we'll compare that with the iTrace, the isotope-enabled transient climate evolution simulation, which is the first one for the last deglaciation, conducted using CESM 1.3. The next thing is in iTrace, the different forcing like changing ice sheet, optical forcing, greenhouse gases, and meltwater forcing are applied additively to the model. So we can isolate the impact of each forcing by subtract these sensitivity experiments from each other. And to further investigate the hydrological processes impact the water isotope signal, we conducted two water tacking simulations for last glacial maximum and early Holocene using ACAM5. We have 25 regions in total, and since we're focusing on the local forcing and tropical Atlantic impact, here we're focusing on the two regions. One is the continental South America, one is equatorial Atlantic Ocean. We can see both of these two regions contribute substantially to the precipitation in tropical South America. Okay, so let's look at the data model comparison first. The background shading represents the mean annual delta 18 anomalies during LGM relative to early Holocene. Clearly, there is a east-west dipole. There are more depleted precipitation over the western Amazon and the tropical Andes, and enriched delta 18 precipitation over the central and eastern Amazon basin, along with the northeast Brazil. And that is generally consistent with the proxy records from this region. So the results of a data model comparison give some confidence to move on to look at the mechanism. So the first thing we want to figure out what's the primary forcing. We compare the impact of optical forcing, greenhouse gas concentration, and also impact of ice sheet to the full forcing simulation results shown in this slide here. And we found the optical-only simulation results, the impact of optical forcing show almost identical pattern compared to the full forcing simulation. So this indicates the optical forcing or precessional forcing is the main driver of the dipole pattern. And we further look at the seasonal analysis results, and we found the DJF, delta 18 precipitation, show a very similar pattern with the annual precipitation delta O18 value in response to orbital forcing. So this makes sense because this is a monsoon mature season, and we know a lot of precipitation concentrated in this season. And that indicates the impact of a South American monsoon. I think that's true because we also found the stronger South American monsoon during last glacial maximum in response to orbital forcing. As we can see, there is a increased precipitation over the western Amazon, tropical Andes, and also the southeast Brazil. And we see the strong South American low-level jet, and we see there is a weaker precipitation along with weaker convection over the northeast Brazil and also the central and the eastern Amazon. So this is a kind of consistent with previous studies showing the role of the change in the South American summer monsoon, how that impacts the precipitation pattern. But we extend our analysis to a broader scale. We look at the and we found there is an Africa-South American intercontinental teleconnection. So the figure here shows the December, January, February equatorial vertical velocity profile in response to orbital forcing. And we see there is a strong convection over the equatorial Africa, and there strong substance over the western equatorial Atlantic and northeast Brazil, and further west there is a strong convection over the western Amazon. And this large-scale circulation largely contributed to precipitation pattern. So we can put together the precipitation, the vertical velocity at 500 hectopascal, and also the Maucher budget analysis results. So we see there is a wetter condition over the equatorial Africa, consistent with a stronger convection here, and we see there is a drier condition over the western equatorial Atlantic and also the northeast Brazil, consistent with stronger substance over this region. And our Maucher budget analysis suggests that the precipitation pattern is largely related to dynamical processes. So the agreement between the precipitation pattern, the vertical velocity, and also the Maucher budget analysis suggests that the precipitation pattern is strongly linked to the large-scale Walker circulation anomalies over the tropical Atlantic. Okay, so why there is a Walker circulation anomaly there? So that is related to the surface temperature over the tropical Africa. So the figure here shows the surface temperature, DJF, in response to orbital forcing, and we see there is a strong warming over the North Africa. So this is because the increased solar radiation on the incoming solar radiation at the top of the atmosphere is further amplified by stronger downwelling long-wave radiation. So that's why the warmest temperature occurred over the North Africa. And the warmer temperature reduced stronger low-pressure system, and that induced the stronger convection over the equatorial Africa. And that further triggered there's a subduction over the western equatorial Atlantic. So that established the Walker circulation anomaly over the tropical Atlantic. Okay, so now we show the teleconnection contributed to precipitation pattern. Will that also impact the isotope composition of precipitation? So we need to look at the water tracking simulation results. So again, we focused on the continental South America, equatorial Atlantic Ocean, and we found the Maucher originated from the continental South America, largely explain the precipitation isotope change from all the 25 regions. And for the equatorial Atlantic Ocean, we found that mainly contributed to the dry pole, the more enriched delta delta 18 precipitation over Amazon and northeast Brazil. And we further decompose the precipitation isotope change into change in the moisture source location, change in the pure delta 18 precipitation composition change, and we further decompose the pure delta 18 precipitation change into change in local condensation, source composition, and the en-route rainout. So I won't explain all the figures, but I have a summary figure here. So we can see there are impact from both local forcing and remote forcing. So during LGM, the South American summer monsoon is stronger, so that's why we see there is a stronger convection over the western Amazon and the tropical Andes, and that contributed to more depleted delta 18 precipitation. And on the other side, the stronger substance contributed to more enriched delta 18 precipitation over the central eastern Amazon and northeast Brazil. So this is more about stronger South American summer monsoon, the local zonal circulation, and how that contributed to precipitation isotope composition. But there's another forcing from the teleconnection. Teleconnection between Africa and South America resulting in a strong substance over the western equatorial Atlantic. And also there's a weaker ITCZ. Both of them contributed to weaker convection and more enriched precipitation composition of the precipitation delta 18. And because of the more enriched water vapor is delivered into the Amazon and northeast Brazil, and that's how the remote forcing play a role here. They contributed to the more enriched delta 18 precipitation in this region. Okay, so I think, yeah. So let's go back to those three questions where we begin with. First of all, what is a dominant external forcing driving the optical scale east-west dipole during the last declination? It's the precessional forcing based on our single forcing analysis. And the second question, how do local and remote forcing influence the precipitation pattern associated with this, the dipole pattern? The dipole pattern reflects the combined effects of a strengthened South American summer monsoon driven by local summer insolation and also a worker circulation anomaly associated with Africa, South America teleconnection. And the third question, what are the key physical processes controlling the spatial pattern of delta 18 precipitation? The strengthened South American summer monsoon influenced the delta 18 precipitation through local condensation change. That's based on our water tagging experiments. And the equatorial Atlantic moisture contributes through change in the moisture source location and also especially the source delta 18 composition. Yeah, thank you. I'll be happy to take any questions you have.
Thank you, Xiaojing, for the nice presentation. Unfortunately, we are running out of time. If you have a question, please find Xiaojing during the break. We will move on to our next talk from Anson.
Thanks for being here to listen to my presentation. And my talk is really similar to Xiaojing's talk, but if you think of a geologic timescale from deglaciation, next is the Holocene. And this is work that I am working at, the work I've been doing at the University of Albany in collaboration with Zhu Chang, Maitlan Bayans, and Matthias. So hydroclimate in South America is very important for many reasons, but I'm going to highlight two of them, one being supporting the biodiversity there, and also two being sustaining regional socioeconomic activities. So you can see at the background on the left, there's lots of, it's really biodiverse and really rich in different kinds of species because it's part of Amazon rainforest. And then it's also one of the major carbon sink on Earth. So hydroclimate changes could definitely affect both, but on the socioeconomic side, people also rely a lot on water for subsistence and also agriculture, as well as hydroelectric power. So because of these importance, we want to understand how hydroclimate in South America changes over time and space. So as Xiaojing mentioned a little bit earlier, we have kind of decent sense of the large-scale circulation and how it works in South America. So here I'm showing on the left-hand side sort of a summary figure of how the large-scale system works. We have the ITCZ here, where it brings in moisture, and then you have the Andes here, which blocks the moisture and then goes southeastward, which is called the South American low-level jet. And then there's also the tropical, extratropical interaction, where the South SAZZ convergence zone here. And then the background color shows you the relative ratio of December to February precipitation compared to the annual precipitation. And as you can see here, in most regions, it's really blue. That means most rainfall happens during December to February, which is austral summer. And if you take a slice over this transect, this is how it looks like. Where you have on the Andes at here, and then you have the low-level jet coming out, and then you have convection here happening in the Amazon, and then what Xiaojing mentioned, there's also the Bolivian high, and then the Nordeste low further out. So because of its seasonal cycle, seasonality, and then which we can think of it as being affected by insolation. We can also look into Holocene timescale then and think about that's when the insolation has changed, summer insolation has changed. Here I'm showing a figure showing the January insolation anomaly from the left, early Holocene to the present on the right, and then on the y-axis is showing the changes by latitude. And one thing you can see here is that in the South America, tropical and subtropical South America region, we see a slow increase in January insolation over time towards present. So if insolation is a dominant factor in driving it, then what we would expect is the rainfall will increase also. So one way we can try to test this and try to figure out whether that's the case is to look into proxy records. And what people are particularly interested in is to use water isotopes and measure the water isotopes in proxy records because they a lot of times reflect large-scale hydroclimate changes. And in fact, people have done it a lot of places, and here's a figure showing the records people have published and generated in South America. And then by doing an ELF analysis, what you can see is a principal component matches really well with the January insolation shown here from the early Holocene on the right towards late Holocene. But while it matches really well temporally, one thing you'll notice is if you look at the loadings here, which each dot shows represents one record. A lot of them on the x-axis is PC1 shows a positive number, so that tells you the changes in those locations correspond to this change. But at the same time, you'll see lots of places where it is more closer to zero or even negative. So that tells us that while water isotope proxy records should record hydroclimate, and that we expect that hydroclimate rainfall should have increased during the Holocene, it's telling you a slightly more complicated picture. So one way to resolve this is to look into climate models, and people in fact have looked into monsoon changes or South America hydroclimate changes over the past 40 years from the early 80s about monsoons to different versions of PMIP models and also more idealized simulations looking at the isotopes. And as well as transient simulation using the Trace21K. But there are a few things that don't allow us to fully resolve or understand what is happening here during the Holocene. So it can be summarized by 3 descriptions. So a lot of time are time slice simulations, some of them are idealized, and then even if they're transient simulations, they're not isotope enabled. So what can we do, and what can we better resolve this? So one way to do it is to look at an isotope-enabled version of fully coupled transient simulation of the Holocene, which was done by Ball et al. And published in 2025. So this model uses the CESM isotope-enabled version CSM1, and then it simulates changes from the 11,000 years before present towards the present, and then it's an extension of the simulation that Xiaojing mentioned, where it incorporates greenhouse gases, orbital forcing, ice sheets, and also freshwater forcings. So for my analysis, I look at particularly decadally average data because that's what's available for now. And then I also look at a December to February period because most of the rainfall happens during that period. So aside from the models, we also want to look into proxy records. So I found all the proxy records that are water isotope based, and then it's in the southern hemisphere of part of South America in the tropical region and subtropical regions. And in total, I found 19 records. So these are 3 questions I want to ask. So first of all, how did the rainfall or hydroclimate change in South America during the Holocene? And then second, to what extent do water isotopes contractually track rainfall amounts? And thirdly, what are the proxy records recording over time, and what do those changes mean? So let's go on and look at the first question. But before that, we actually want to make sure the model is doing something similar or what we would expect. So to do that, I compare the model with the proxy records in isotope space. And then you can see here on the left-hand side is the correlation coefficient between the proxy record and the data. They look okay, like most of them are red. And then on the right-hand side is the root mean square error. It varies by a bit, but then the takeaway is that there's no systematic error or discrepancy between models and proxies. So then we can go ahead and look at quantify hydroclimate change. And one way to do it is to look at the precipitation minus evaporation of specific regions over the full atmospheric column. So when you think about the P and E, P minus E over a column, atmospheric column, it can be driven by change in the moisture advection. So that's a divergence of Q, which is a specific humidity. And then it can also be driven by changes in mass divergence. So divergence of UK, and then also there's a residual term. And when we take this, do the calculation, and then plot it and compare the present day versus early Holocene, and this is how it looks like. On the left-hand side is the P minus E, and then we have moisture advection, mass divergence, and then residual terms. And what you can see here is that visually speak, you can see P minus E and the mass divergent terms match, has a batch match, which tells us that mass divergence probably dominates in controlling the P minus E in this region. And when we think about the mass divergence, it can be further broken down into 2 terms where we can think of it as the mass divergence driven by varying moisture. So you change the Q, but it's still more circulation-driven changes. But you can also fix the moisture. You don't change the moisture, but you're changing the mixed up. And then you can change the circulation. This is mixed up. So in some ways, you can think of it as a dynamical change or in thermodynamical changes. And when you break it down again, here you can see that for the mass divergence terms, it's mostly corresponding to the circulation change, which tells us that from early Holocene to late Holocene, there's an increase in rainfall, or it's getting wetter partly because of the circulation is changing. We can look at it also on a temporal view where I took a box average of this region, and then we look at P minus E, moisture advection, and mass divergence, and this is consistent with what I just showed you in the spatial view. The interesting part is here when we look at the circulation change in humidity part, where if you look at the right-hand side on the time series, you will see that while the purple and green vary together mostly, but during the earlier Holocene, you see that there's an increase in the moisture part where it's mostly driven by humidity. So this tells us and shows that humidity matters as well. So this kind of addresses the first questions I have. So then now, since we mostly use water isotope proxies to understand past hydroclimate change, we want to understand whether water isotopes actually track rainfall amount, which for paleo people, we call that as the amount effect. So to do that, I extracted the dominant covariant trends in the delta 18O precipitation and also precipitation from iTrace. And then I'm only showing you from 8,000 years before present to 0 to present. And you can see there's an increasing trend over time, which is consistent with what we think about precipitation. It's getting wetter. But what we are particularly interested in is the relationship, covariant relationship between the oxygen isotope and precipitation. So meanwhile, in some regions, such as the western part of South America, you see a negative relationship. So purple and green here, and then in the Nordeste or like eastern Brazil region, you see brown and orange here. That tells you a negative relationship, and which indicates an amount effect. There are a lot of other regions where you see that it's green here, so positive, and also orange here, that means it's positive. So what this tells us that while the oxygen isotope in precipitation tracks rainfall fairly well in some regions, this relationship varies quite a bit over space and doesn't really track rainfall. So then that gets to the questions of what are the other proxy records that don't really track rainfall? What are they recording? So to do that, understand that I looked into, go back to the proxy records, and then I did a cluster analysis to try to separate them into different temporal patterns. So you can see here that there are 3 different clusters that I found in the proxy records, where we have cluster 1 where it's going from more negative to more positive towards present, cluster 2 going from more positive to negative, and then cluster 3 is kind of getting more negative, but also a little bit mixed. And interestingly, if you look at the spatial pattern, you will see that some of them are kind of clustered together. So cluster 2 is mostly in the western part of South America, whereas cluster 1 is mostly in the eastern, and then cluster 3 is more in the southeastern region. Okay, so then I did the similar thing. We found that it's similar in the model so that we can use the model to try to interpret it. So now we first look at cluster 1. This is when it gets more positive. And if we look at the first place, this is, I did a regression of this cluster time series with precipitation and shows a negative relationship that tells you that's kind of an amount effect. And in fact, if you look at the vertical circulation pattern, that's consistent with what Xiaojing showed of having a Bolivian high and then also subsidence in the Nordeste flow, which causes drying and more positive relationship between more positive delta 18O. And then, but then if you look at this region, it's more positive. There's a positive relationship between rainfall and isotope. That means it's more complicated. And so to understand that, we have to look back into sort of visually try to look at the moisture source, which mostly comes from the South Atlantic here. This is a modern condition, and when we look at the changes over time, we see that in the isotope space, it's getting more positive over time, which means that the isotope in the vapor source is responsible for making this more positive. And if we look, and then now if we look at cluster 2, we see a more negative relationship between precipitation and isotope, which we can simply think of it as then as a local rainfall effect. And then on top of that, since we know that the moisture circulation matters a bit, so we find that the moisture, there's also a relationship with the South American low-level jet, which could drive a negative relationship, more negative precipitation isotope. And lastly, this is the third cluster where we see there's kind of like a negative relationship between delta 18O and precipitation, but it's relatively weak. And then we also know that this is more in the subtropical region, so that there's less convection. So that means we also, again, need to look into the moisture advection. So since this is mostly coming from the south, the low-level jet, that means that there's also a relationship between the low-level jet and the isotope in this region. And this kind of addresses what I was trying to ask here, and then this is my conclusion here. Thank you.
Thank you, Anson. Unfortunately, we are running out of time. If you have a question for Anson, please find him during the break. We will move on to our next talk from Maya.
Hi, Hi, thank you all for coming. I'm Maya. I'm a second-year PhD student at the University of Arizona, and today I'm going to talk about how paleoclimate data assimilation can produce a mid-Holocene thermal maximum. Yay, okay. So looking at this plot, we see here the Holocene temperature conundrum. We have anomaly, global mean surface temperature anomaly from the pre-industrial on the y-axis, and time on the x-axis going from the LGM all the way on the left to the present all the way on the right. And you can see that our proxy records, which are in blue here, show warming from the LGM to the early Holocene, and then a temperature maximum at the mid-Holocene around 8,000 to 6,000 years ago, and then cooling to the pre-industrial. But our models, which we can see here in yellow, black, and gray, show gradual warming from the LGM to the pre-industrial. So in models, the PI is the warmest part of the Holocene instead of the mid-Holocene. When I say PI, I mean pre-industrial. So this is kind of concerning to us as paleoclimatologists, right? Because if our models and our proxies don't agree, it implies we're missing some kind of process in them. And that's what we use to understand the climate system. So one of the ways we can try to resolve this is through data assimilation, offline paleoclimate data assimilation. I find when I talk to climate scientists who work in the modern, they don't understand what we're doing with paleoclimate data assimilation, and when I talk to paleoclimatologists, they don't understand from the other direction. So I'll try to spend a lot of time on this slide. So we start with both climate models of our target time period and paleoclimate data from our target time period. Our climate models, we have an ensemble of simulations of that target time period, and that makes up our prior state, or our x-prior. We also have paleoclimate data from our target time period. And what we do is we transform our x-prior into proxy observation estimates, or what a proxy record would look like if the model made it up using proxy system models. So if you're a paleoclimatologist and you think of the systems of equations we use to transform, say, d18O of a foraminifera shell into sea surface temperature, we're kind of going in the opposite direction there. Once we have those proxy observation estimates, y hat, we can compare them to our actual proxy records, y. And if you look down at these equations at the bottom, I don't know if I can, yay, okay. So we have the equation of our data assimilation right here, which is a Kalman filter. We have the difference between our actual proxy and our proxy observation, weighted by the Kalman gain. We add that to our prior ensemble state to create an ensemble of updated posterior states for our target time period. So the Kalman gain considers the covariance of our prior state and our proxy observation estimates together. So that's kind of saying how informative do we expect this proxy record to be for a specific climate variable. And then it also considers the covariance of our proxy observation estimates together. So it's kind of saying how much are these similar across our model ensemble, how much do we trust the model, as well as considering R, which is an error we assign to our proxy system models based on our knowledge of them. So we can look at some previous data assimilation efforts in the mid-Holocene. I'm sorry the shading on some of my things is not showing up very well here. You'll just have to trust me. We can look at these lollipop sticks here, which are two data assimilation efforts from the mid-Holocene to the pre-industrial. We have mid-Holocene to pre-industrial global mean surface temperature anomaly on the y-axis. And we have Erb et al. From 2022, which shows about 0.1 degrees warmer mid-Holocene than pre-industrial, and Osmond et al. 2021, which shows a mid-Holocene that's about 0.2 degrees colder than the pre-industrial. Both of these don't approach the warmth reconstructed by our two major proxy compilations from Marcotte and Kaufman, which you can see up there. They're hovering around a ½ degree warmer mid-Holocene than pre-industrial. So we tried a more expansive approach with this data assimilation. We used the sea surface temperature proxy compilation gathered by Osmond et al. 2021, which integrates 4 sea surface temperature proxies, UK37, magnesium, calcium, D18O foraminifera, and Tex86, and those are in warm colors. and 3 terrestrial proxies, D18O of ice cores, of speleothems, and delta D of leaf waxes. You've been hearing a lot about those in the last couple of talks, but they integrate water isotope ratios in precipitation and can be linked to a variety of climate variables, and those are in cool colors. So we have more than 1,000 proxies in the pre-industrial and around 800 in the mid-Holocene. Our prior is primarily composed of a perturb-parameter ensemble using the NASA GISSI 2.1G model. You can see these maps here show the mid-Holocene to pre-industrial surface temperature anomalies for each parameter. The parameters in this instance aren't that important. They alter clouds and convections, but mainly what this is providing for us is a prior with a wide spread of equilibrium climate sensitivities, surface temperature states, and precipitation states. And to that, we also add other isotope-enabled models, including some from AWI, MPI, and 2 versions of ICSM. And thank you to everyone who gave me climate variables from their models. So one of the things we see can be super influential in our prior state, especially for the mid-Holocene, is the kind of vegetation we prescribe in the mid-Holocene. So we can look at this study from Thompson et al. In 2022. Oh no. And if you look here, you can see this dot here at the mid-Holocene 6,000 years ago is global mean surface temperature. This is all an anomaly to the pre-industrial when we use pre-industrial vegetation in a mid-Holocene simulation. So you see that's colder than the pre-industrial. But if we add in vegetation we might consider more accurate to the mid-Holocene, and there are 3 different options for that here, we get warmer and warmer temperatures, mostly due to a decrease in albedo over those areas where we're adding vegetation. So that's very important, the kind of vegetation you have in your mid-Holocene prior. And when we look at the priors used in these data assimilation studies, we can point out some of the reasons that there might be differences in their mid-Holocene to pre-industrial global mean surface temperature anomalies. These are just the priors, these are not the assimilations, and I'm showing a 95% confidence interval for each. So, sorry again. In the herb study, we have a relatively narrow prior with a cooler mid-Holocene than pre-industrial. In his case, he used only models where pre-industrial vegetation was used in the mid-Holocene. In Osman's case, he used a mix of both, and they have a warmer mid-Holocene than pre-industrial. And in our case, we also use a mix of both, and we have the broadest prior of all 3 of these studies, mostly due to the wide variety of models we use. So you can look again at the priors we're using in this study. At the top left, we have the GISS ensemble mean, and you can see it's quite warm in the mid-Holocene to pre-industrial. We have AWI, MPI, and 2 ICSM members that are all cooler. Those all use pre-industrial vegetation in the mid-Holocene. And then the ICSM member at the bottom right uses mid-Holocene vegetation, or a greener mid-Holocene, and you can see it's warmer in the mid-Holocene than the pre-industrial. So when we look at the assimilation anomaly that this produces, the mid-Holocene to pre-industrial assimilation, we've got a global mean surface temperature anomaly of about 0.3 degrees, so a warmer mid-Holocene than pre-industrial. And we can see particular warming on the Canadian Shield, in the Arctic, and over the Southern Ocean and Antarctica. When we look at this, I didn't have time to put validation slides in here just because it's already kind of a long talk, but when we look at this against validation data, the TEM12K data set, as well as precipitation and precipitation minus evaporation data from different kinds of proxies, we see this assimilation performs better than the prior ensemble mean. So why is this assimilation warmer in the mid-Holocene, and the other 2 don't approach the warmth of our proxy compilations? We can kind of do ad hoc sensitivity tests that sort of mimic the experimental setups used in these assimilations to try to get an answer for that. So in Osman's case, they only use marine proxies, the same marine proxies we use in our study, and they use mixed mid-Holocene and pre-industrial vegetation in the mid-Holocene. When we do that, when we assimilate with sea surface temperature proxies only, we get a global mean surface temperature difference of less than 0.1 degrees warmth in the mid-Holocene with a pretty wide standard deviation spread. So here we're saying that it's our terrestrial proxies that are really strong constraints on mid-Holocene warming. We can also look at ERB. They use a mix of marine and terrestrial proxies, with a majority of them being terrestrial, and they only use mid-Holocene priors that have prescribed pre-industrial vegetation. So when we use only members in our mid-Holocene that have prescribed pre-industrial vegetation, we get a quite cold mid-Holocene. This is really not an apples-to-apples comparison because our proxies are very different, and this is a relatively narrow ensemble in my case, but it is informative that accurate vegetation is also a strong constraint on mid-Holocene warming. So we can get to the end of this talk here, and we can see that my data assimilation, global mean surface temperature anomaly, it approaches the warmth of these two proxy compilations. You maybe can see the range of the Marcotte and Kaufman standard deviations here, but it is within the range of both of them, which is great. But I will say, you know, this study really shows that you have to have a lot of nuance in your work, and I would also like to have a lot of nuance in my work. So I'm going to continue to investigate how these water isotope proxies are informing mid-Holocene warmth. I think that's really important. And I would also like to point out that the mid-Holocene greening efforts in my priors don't have a lot of nuance, and they might be wrong in some places. So I'm planning to run Biome 4 off of my assimilation product in the mid-Holocene to see if we can get at more accurate vegetation in the mid-Holocene. That's all I have. Thanks so much.
Great talk, Maya. I have a lot of time for questions. Charlie.
Hi, Maya. Thanks. That was very cool. I was curious, I guess I was surprised at how big an impact the terrestrial proxies had compared to the last glacial maximum reconstruction or reanalysis. So I was wondering, because they were just precipitation terrestrial proxies, right? No temperature. I was wondering if you had a sense of dynamically why that might be important in a region like the Canadian Shield, because it seemed like a lot of the monsoon regions weren't as affected by that. And so I was just curious if you kind of had a sense of what you expect to see when you look into that more.
Yeah, definitely. So one of the limitations of doing time slice data assimilation is that we really do have to make sure that the covariance structures of these variables make dynamic sense. And I'm still drilling into that. What I can say now is that there's pretty strong covariance between temperature and DAT-NO of precipitation in these higher latitude regions, as you might expect dynamically. If there are warmer temperatures in mid-Holocene simulations that have Arctic greening, you might expect changes in isotopes in precipitation. But I definitely want to make sure that this mid-Holocene warming is not just an artifact of that strong covariance and is dynamically connected. So I'm still thinking about that.
I had a question about, so you mentioned briefly that the Herbidol used a pretty narrow prior ensemble and that might have affected their posterior. Is the idea, I guess more generally, like, do you just always want a broader prior? Like, is a broader prior always better? Or is there some point at which it becomes too broad and you don't want to keep throwing models into your prior, or different configurations rather? Yeah.
An interesting question. I think in my experience, if you have proxy data that are pretty informative to your time slice, you will get similar results regardless of your prior. So for example, I've been doing some similar work in the last glacial maximum, and I get pretty similar results to Jess Tierney's work from 2020, even though she used a CESM prior and I'm using this GIS PPE. But I think also using a broad prior gives us, like, it makes it that we don't have to be so worried about the inherent biases of one model. And I don't think I would say, I don't think I would have like a situation where I wanted to use a narrower prior for some reason unless I was looking at a model output and thought it was incredibly unrealistic or unphysical. Yeah.
That makes sense.
I don't know if you have a different opinion.
No, I guess like I'm curious, using different models, whether your final product blends the covariance of two different kinds of models that might have different like end-to-tail connection or something, and like that might give you a weird, I don't know, yeah. Maybe you have enough data that that's not a problem, but I guess if there are cases like that where.
Yeah, that's definitely something we think about, and that's something we can try to maybe get around through varying localization, varying how much the proxies can affect different climate variables in the posterior, and seeing if, like at different localization radiuses, we have artifacts that may seem to be connected to one particular model.
Thank you so much.
Yeah.
I have a quick question about the seasonality. So do you reconstruct the seasonal temperature as well? Because the seasonal temperature is a part of the Holocene temperature conundrum.
Definitely. I haven't yet. I'm just getting back to this work after my comps, but I'm going to look into that. Yeah.
Okay, let's thank Maya again, and let's move on to our next talk. Our next talk is from Go.
Hi, everyone. My name is Go. I'm a second-year PhD student at George Mason University. Thank you for giving me this opportunity to share our work on physical mechanisms of extreme meso events during the mid-Holocene climate. Right. Yeah, so I'd like to start with answer diversity. So I have linear stream for time series here to show strong interannual variability in terms of both positive and negative resistivity anomalies. And then if we focus on some changes in spatial patterns, for example, strong El Nino from 997 and the following La Nina, we can see very different spatial pattern of resistivity anomalies. And then these changes in both spatial pattern and amplitude can be also seen from this, this figure, which shows historical meso events in terms of their longitudinal distribution of resistivity anomalies. We have strong El Ninos, also we have Central Pacific El Ninos, and then we have La Nina events. They have really different spatial patterns. Therefore, here I'd like to point out the importance of meso diversity, which means both spatial pattern and amplitude of meso events vary among events. So as Enzo and Maya touched, I'd like to move on to the mid-Holocene, which is approximately 6,000 years ago. Due to the precessional change, this 6K experienced warmer summers and colder winters than the present climate in the northern hemisphere, while southern hemisphere experienced reduced seasonality. There are a few studies trying to understand the changes in extreme El Nino events during the 6Ka. So on the left, one study tried to figure out the frequency of different frequency of extreme El Nino events among different climate mean states, and it turned out 6Ka had a reduced frequency of extreme El Nino compared to pre-industrial or warmer climate. And on the right, there's one possible mechanism to explain these changes, which starts from anomalous westerly winds over the Western Pacific, which initiates downwarding Caribbean wave to the east, which reduced the stratification and deepened the thermocline. Therefore, we had reduced the variance of Eastern Pacific El Nino events. Then, as Maya touched this, we had another significant feature of 6K, which is Green Sahara. If we compare precipitation, summertime precipitation anomalies between mid-Holocene and pre-industrial climate, we can see increased precipitation over Sahel and Sahara region, which indicates intensified West Africa monsoon. According to other proxy records, this intensified West Africa monsoon resulted in changes in the vegetation covers, specifically present-day Sahara. These are used to be covered by grasses and shrubs. Therefore, Green Sahara contributes to more intensified precipitation pattern here, and this is already important another significant feature. Yeah, all right, so the objective of the study, even though there are some previous studies trying to understand the changing extreme El Nino events, I'd like to point out that the changing La Nina types have been largely excluded. Therefore, we'd like to investigate both extreme El Nino and La Nina events in this study. And then we are also including Green Sahara effect to ensure a more realistic representation of extreme N types during 6Ka. And then we investigate the underlying physical mechanisms by quantifying the contribution of coupled ocean-atmosphere feedback. So we use the outputs of iStop CSM version 1.2. We have PI control and then two different 6K simulations. The first one is orbital simulation, which basically follows the PME4 protocol. The other one is orbital plus Green Sahara simulation, which also incorporates Green Sahara forcing. And then hereafter, we are just focusing on this orbital plus Green Sahara simulation to look at 6Ka. And then why we can focus on orbital plus Green Sahara simulation, here we are comparing the SST-based standard deviation reduction by PME4 models and then iStop-based standard deviation reduction from proxies and then to 6K simulations. These are all over the Central Pacific. So we can see that orbital plus Green Sahara simulation shows better agreement with proxy records compared to orbital simulation or even other PME4 models. Therefore, we can just focus on this orbital plus Green Sahara simulation to look at extreme N types during 6Ka. Then how to detect different extreme N types? So previous studies largely depend on E and C indices, but I'd like to point out that these indices cannot capture La Nina types. And also, most of the time, these indices are calculated separately in each time period, so we cannot directly compare the results. Therefore, we are introducing Gaussian mixture model clustering, which gives us the probability distribution over the on the latent space expressed as a mixture of Gaussians as the schematic figure on the right. Let's say data set A is PI control, data set B is 6Ka. This method can give us this different multiple Gaussian distributions. And if you can use the same Gaussian distributions among these two periods, so we can kind of compare directly. Also, it can also give us La Nina types. And in order to understand the underlying physical mechanism, we are applying the mixed layer heat budget analysis. Here, I just picked up some important terms to look at. And so on the left, the first one is zonal advective feedback. And also we have thermocline feedback and upwind feedback. These terms are averaged between June and November to look at the ENSO development phase. Also, finally, these terms are all averaged over the main region for each ENS type by detecting the largest SST anomaly point in the composite SST pattern. All right, so based on Gaussian mixture model clustering, we are able to capture 4 different ENS types. The first type shows strongly positive SST anomalies over the eastern to central equatorial Pacific. Therefore, we named this extreme El Nino. We have moderate positive SST anomalies over central Pacific in the second pattern. Therefore, we named this CP El Nino. We also have CP La Nina, which shows moderate negative SST anomalies over the central equatorial Pacific. The last pattern shows basin La Nina, which shows strongly negative SST anomalies across the basin, especially over the western to central Pacific. Then how did it look like in the mid-Holocene? So we can just compare the first column and the second column. Extreme El Nino showed significant weakening, especially over the eastern Pacific. Also, basin La Nina showed also significant weakening, especially over the western Pacific. So based on these results, we got 2 extreme ENS types. The first one is extreme El Nino, and the second one was basin La Nina. So we're gonna focus on these 2 ENS types. So as I explained, we are using the mixed layer heat budget analysis. And then first for extreme El Nino, we have term A, temperature tendency. Positive means there's a development of positive temperature anomaly. And then that can be largely explained by thermocline and upwind feedback. This makes sense because the main region of extreme El Nino is eastern Pacific, so the thermocline is relatively shallow, so there's big impact from these 2 vertical feedbacks. There is still some impact from zonal advective feedback. And if we compare PI control and 6K, we can see the reduction of temperature tendency. Again, that can be largely explained by these two vertical feedbacks. Moving on to baseline La Nina, now we have negative temperature tendency, which indicates the development of negative temperature anomaly. That can be largely explained by zonal advective feedback, which is consistent with the main region of baseline La Nina, which is over the Central Pacific. Therefore, thermocline is kind of deep, but there's big impact from zonal advective feedback. But still, there's some impact from thermocline feedback. Then this reduced temperature tendency can be, again, largely explained by this zonal advective feedback. Then, okay, so why were the oceanic vertical or zonal advective feedback suppressed during 6K, like these three feedbacks we saw in the previous slide? Can we answer this question by focusing on their linkage to changes in the mean state? Yeah, so first we're gonna focus on the first two vertical feedbacks. Here I'm showing the climatological thermocline in the PI control as orange and then in the 6K as green. We can see thermocline was deepened during 6K, especially over the Central Pacific area. Therefore, deepened thermocline limited the impacts of thermocline variability to the mixed layer. Therefore, it can explain reduced thermocline feedback in the first bullet point. And the second point is that deepened thermocline also means vertical temperature gradient was smaller. Therefore, if you just focus on this term, we can also explain reduced opinion feedback during 6Ka. We can also look at some other variables such as surface temperature and wind anomalies during springtime, wintertime anomalies in panel B. Panel C shows summertime vertical velocity anomalies. Blue means anomalous upward motion, and red means anomalous downward motion. So from panel A, we can see anomalous vessel winds over the Western Pacific, which initiate downwind Kelvin wave to the east to deepen the thermocline. This is consistent with one possible mechanism I introduced in the introduction section. And also at the same time, during winter time, we can see South Pacific as warmer. In general, the water from this region is subducted to the equator. Therefore, if warmer water is subducted to the equator, that can also reduce the stratification. In other words, it can also help explaining thermocline deepening. And interestingly, from panel C, we can see anomalous upward motion over the Western Pacific and anomalous downward motion over the Eastern Pacific, which pretty much means strengthened local circulation over the Pacific. That can be also seen from strengthened trade winds at the surface. Then in this slide, we are trying to understand the meaning of strengthened local circulation. Here, I'm showing the wind stress anomalies as vectors and the wind stress curve anomalies as shading. Over the equator Pacific, we can see kind of clockwise wind stress vectors, which indicates negative wind stress curve anomalies. That is clearly consistent with this blue color shading. And if you then based on this severe drop transport, if there is negative wind stress curve, there should be southward motion of water. Then if you compare this negative wind stress curve to the north of the equator with the south of the equator, the north of the equator shows more significant negative wind stress curve anomalies. Therefore, I just put the schematic figure on the left. There should be the convergence of water along the equator during 6Ka. Actually, that can also help explaining the thermocline deepening during 6Ka. Now we understand these two vertical separation of these two vertical feedback during 6Ka, and let's move on to the suppressed zonal advective feedback. Here I'm showing the composite oscillator mechanism of extreme El Nino and baseline La Nina from December -1 to all the way to December +4. Blue dashed line is SST anomaly, red line zonal advective feedback, and then pink is the zonal current velocity. So from panels A, B, we can see during PI control, extreme El Nino transitions to La Nina in the following winter, while during 6K, that transitions to just neutral. Therefore, the first bullet point, we cannot see the transition from extreme El Nino to La Nina during 6Ka, which should indicate that weakenings of heat content and zonal current after extreme El Nino or before baseline La Nina. Then here I'm showing panel CD, especially the purple line. Before baseline La Nina, there is a big swing from eastward zonal current to westward zonal current before the peak of baseline La Nina, but that is also gone during 6Ka. Therefore, this, we cannot see the strong transition from eastward to westward zonal current anomalies before baseline La Nina. This directly affected the weakening of this zonal advective feedback as shown in this red line. Now we understand that This significant transition from El Nino to La Nina resulted in the weakening of westward zonal current anomaly that can explain zonal weakening of zonal adductive feedback. All right, to summarize, for the first time, we compared the Green Sahara forcing into ICSM to look at ENSO diversity during 6KA. Then we are able to capture not only extreme El Nino, but also baseline La Nina. And then focusing on mixed year heat budget analysis, we are able to understand that weaker extreme El Nino can be primarily explained by weaker thermocline and upwind feedbacks, while weaker baseline La Nina can be mainly associated with weaker zonal adductive feedback. Focusing on the linkage to the mean state, the deepened thermocline can explain reduced thermocline and upwind feedback, especially during extreme El Nino. While weaker westward zonal current anomalies, which is associated with weakened instant transition, can explain reduced zonal adductive feedback, especially during the baseline La Nina. Still, we are interested in the impacts of these weakened different ENS types on their different precipitation patterns, especially such as like North and South America. So yeah, this is our next step. Okay, I will stop here. Thank you.
Great talk, Go. Do we have questions for Go? Do you have questions online? Maybe I can ask a simple question. I think I really like all your analysis. I'm wondering what's the potential implication on our, say, projection of the future and so variability from your analysis?
Yeah, so the reason why I just brought up the changing mean state is because we can kind of compare the changing mean state in the future and the mean state in the 6Ks. For example, we can kind of compare the changing Pacific local circulation or thermocline change in the future. I still need to study that. Maybe if we can compare this mean state, we can kind of see, okay, broad idea of how this ENS diversity will be changed in the future.
Thank you.
Thank you.
Thank you, everyone, for joining the first part of the paleoclimate session here. And I know we are behind the schedule, but please still come back at what time? Please still come back at 3 p.m. And because we have to conclude at 4 for the CESM plenary. And we have 4 exciting talks, so please come back. Yeah.
Okay, let's try to stay on schedule. Thank you so much for coming back to attend the second half of the paleo session. Before we start, I want to remind everyone that after this session, there's the plenary to wrap up the CESM workshop, but then we're having our paleo happy hour at 5:15 at the Pattern Break Brewery. Same one as the reception yesterday. And so, with that, I'll introduce our first speaker of this session, Elke Zeller. Take it away.
Thank you, Sophia. Okay, I'll try to stay on time. Hi everybody. I'm Elke Zeller. I'm a postdoc at the University of Arizona, and I'm going to talk a little bit about vegetation in the Pliocene. This work is part of a pretty big project in which we're gonna, which is called Paleo Weather, and Dan Arnheim made a really cool little logo for us over here. Just want to point this out because I just love this logo. We're gonna do some high-resolution paleoclimate modeling and use proxy data to constrain our climate models with data assimilation. So similar to what Maya was talking about, who is also part of, or going to be part of this project and doing some of the data assimilation together with Fang. And we want to examine past warm periods to use as analog for potential future climate change. So to do this, as Maya already nicely said, we need a big ensemble. And we're going to do different warm periods. I'm sorry. So we're going to do the Pliocene, Miocene, Eocene, and Cretaceous. And we need like an ensemble of. So we need to have a couple of ensemble members. We're going to do cloud parameters, which Xiang is actually working on, and then we have some CO2, and we also want to look at vegetation. So I kind of got tasked with the vegetation because it's something I'm interested in. And then we're using ICSM 1.3. So for here, you can kind of see the workflow for the overall project, but at the moment, we're just over here. So today I'm going to talk about the Pliocene, low resolution, so 1 by 1 degree, ICSM 1.3, and vegetation. The reason we want to look at vegetation is because we see that there's a model data mismatch, and particularly we see this in the northern hemisphere high latitude. So if you see the PMIP model ensemble over here and the proxy data over here, you can see that it's a lot like the dots are a lot more red than in the model. And then, and then Julia Tyndall also did another compilation over here, and you can see also that the proxy data is a lot warmer than the models. So when we look at the normal vegetation forcing that is being used in the Pliocene, it comes from the Biome 4 model, and then they use proxy data to reconstruct global vegetation. But as you can see in Eastern Siberia over here, there are not a lot of proxy data points. So all of like the little dots are where we have data, but proxy data, but we don't really know what was there, or at least when this compilation was made. And Biome 4 predicted that there was grassland over there, so that was kept. But now we have some more data, and Novak et al. Recently came out with a paper which actually showed that there might have been like a lot of forests in the overall northern high latitudes. And then, this is an older paper by Andreev, but it shows that there's cold deciduous forest over there. So I wanted to specifically target this region and look at that. So what I did is I used Biome 4, and I used kind of our control simulation and I ran it through biome 4. So the first time I did this, I got this map, and I still got what everybody else gets, and this is kind of like the grassland up in the northern high latitudes. So you can see the green over here corresponds over here. So then I started talking with Jed Kaplan, who is basically who made this model. So he said, okay, so there are specific phonologies that are hard-coded in the model, so maybe we should look at that. And because I wanted to target the cold deciduous forest, I looked at the needle-leaf deciduous forest, and I changed the upper warm month temperature from 21 to 23, 25, and 30 degrees Celsius. And when I do that, you see that this grassland slowly disappears over here. I compared then our model results with the proxy data, which are all of the dots on the map, and I calculated the Cohen's kappa, and you see that that's at K over here under the degrees Celsius, and you see that that goes up until 25 degrees Celsius, and then it kind of levels out because most of the grass actually disappeared, so we don't really see any improvement. And therefore, I chose the 25 degree Celsius map to go further with. So previously, we saw megabiomes. Now over here are the two different vegetation boundary conditions. In the smaller groups, we call biomes. So sorry, the colors changed. But the big change is this yellow over here, which is grassland from the initial control run, and it changed to this light blue, which is cold deciduous forest. And some other changes are in the mid-latitudes and also some rearrangements, like all globally. But we're just gonna look at the differences between these two maps. So when I compare the temperature, on the top here, you can see our control run minus the PI, and the bottom is our Pliocene vegetation run minus the PI. The warming patterns, they both look similar to what we've also seen in the PLIOMIP2 model ensemble. And we see that the largest warming is over the high latitudes and over land. Then if we compare between these two models, we see that the PLIO-Veg warms about half a degree more than our control run. So we see that with our change in vegetation, we can warm up the whole globe quite a bit. And this vegetation change has the biggest effect in the northern high latitudes. As you see, the warming becomes more over there. Then if we look at the seasonal decomposition, so specifically winter and summer temperatures, we see that the winter warming is located over the ocean mostly, but our summer warming is mostly over land. And then again, we see this half-degree warming for both of the seasons. And the vegetation change in eastern Siberia really enhances the warming in both seasons, but mostly in the winter. So we also looked at the P minus E response. We see drying in the mid-latitudes, and our ITCC shifts northward, and our global vegetation kind of enhances the whole signal we see in our control run. And for the different seasons, we see an increased monsoon precipitation over land, and there's drying in the Arctic in the winter month, which we'll be coming back to at the end of the presentation. And globally, PLIO-Veg still enhances the whole response. I also looked at how our two different models now compare to proxy data. So for temperature, on the left side over here, we have the Plio control minus PI on the top again, and then Plio-Veg minus PI on the bottom. And I'm sorry, the R-squareds are quite small, but we do see that for the temperature, it gets better. And we get more closer to the proxy data. For precipitation, I didn't calculate the R² because we just have either more wet or more dry, and actually most of the proxy data says it gets wetter. So in this figure, all of the triangles are a warning signal, and this is where they do not agree. And you can see that in a lot of places they don't agree. So when we calculate the GWET's AC, it actually is negative, which shows that we are not very close to the proxy data. This is a lot driven by drying we have in the Mediterranean and over Europe, while the proxies say this shouldn't happen. In our plyo veg, it gets a little bit better because it gets less negative, but it's still not very good. So we have to be careful when thinking about P minus E, and we will not talk about this for the rest of the presentation. So our winter warming, I wanted to see where this was coming from. So over on the left side, you can see the temperature by latitude, and our solid line is our annual temperature. Our dashed line is our winter temperature, and the dotted line is the summer temperature, and then green is the vegetation run, and pink is the control run. So you see that in the high latitudes, the biggest difference between the lines actually comes from the winter month over here. And this corresponds when we look at kind of like Hofmüller diagrams for a temperature by month, and by latitude, you really see in the winter month, there's a lot of warming in the Arctic, and then it shifts a little bit lower in the summer months. And then when we really look at what the new vegetation is doing, we see that the warming signal is very much concentrated in the Arctic. So then I wanted to see where this temperature difference is coming from. So on the top row, you see all the seasons and the temperature difference. In the bottom row, the middle row, you see the albedo, and the bottom row, you see the ice fraction, and there's a pink stippled line, and this is the 80%. If ice fraction is above 80%, I made a little like stipples there. So when you compare the temperature with the albedo, you see that they correspond. If the albedo decreases, we see a lot of warming, versus if the albedo increases, we see even some cooling in some regions. So a majority of the warming is driven by this albedo change, but we see also some ice loss over the DJF months. Okay. We see also some ice loss, in the MAM season. No, wait. Yeah, no, I'm sorry. In the winter season, we see that there's a lot of ice loss. And as I mentioned all the way in the beginning, it was very dry. So this is probably because there was not enough precipitation during those months. While in the next season, we actually do see that the ice did come back. So maybe there's a shift in seasonality there, which is something I still need to look at a little bit. So in summary, our vegetation increases the temperature by about 0.5 degrees, and this reduces the proxy model differences. Our winter warming is mostly located in the northern high latitudes, which helps close this difference. And the warming is probably primarily driven by the albedo changes. And we should never forget that vegetation is very important and can do a lot of things. That's it.
Time for one question. Yeah.
I think this is maybe the second or third time I've heard that vegetation is important, and so the question is, what are you going to do about it? And I think it's a feedback thing, right? I mean, you kind of put that in there so that the temperature was warmer because of the vegetation, but actually the vegetation is there because the temperature is warmer. So I guess the question would be, what kind of strategy would you, could you propose to think about that feedback and how strong it is?
Yeah, I think I would really like to do maybe an asynchronous coupling between Biome 4 and CESM, just to see like where is the vegetation pushing the climate and the climate pushing the vegetation in that way. But yeah, I didn't have time for that in this specific scenario. But that is something that I would really like to do, and I think you need like 50 years to get CESM like a little bit stable, and then you need to run Biome 4 again. So it will, yeah. I'm trying to do like back of the envelope calculations to see how many compute hours I need, but I think quite a lot. Yeah.
Thank you, Olga. Let's move on to our next speaker of the session, Durvla Megan Kumar. Thank you.
Thanks. Okay, yeah, thanks everybody. I'm excited to talk about this work in progress today, which is part of, again, this larger group that Elka introduced. So kind of the motivation of this is that there's a lot of interest in understanding how tropical cyclones will change with warming. And this is just a brief overview showing that in general, maybe TC frequencies are not going to increase or maybe even slightly decrease. But if we look at the strongest storms, these are more robustly projected to increase, particularly in terms of intensity and rain rate, though there are regional differences that are still being kind of pieced apart. And so one way that we can understand or contextualize these future projections is by looking at changes in tropical cyclone frequency and intensity in the past. This is called paleotempestology. This is just a diagram showing a variety of ways that people have approached paleotempestology, but the one that I'm going to focus on today is, I think I pressed the wrong button, is this leveraging kind of the delta 18O composition of tropical cyclones. And so, oh, okay. I think I changed the settings somehow. Okay, so in general, the isotopic composition of tropical cyclones, right, I'm just showing this for oxygen, but oxygen and hydrogen or deuterium are gonna follow the same pattern, is more negative than regular rainfall. And so this is shown in the graph on the left just for like an event-based distribution, but then in the kind of time series on the right, you can also see how the general negative trend as over time as you get a TC passing through this region. Okay, and this is Speleothem, which is a cave record reconstructing the delta 18O of precipitation. This is from Belize, I'm pretty sure. And so you can see these negative excursions that are occurring at times of known tropical cyclone activity in the past. So this is really great kind of prior work, but what I'm asking is how robust is the isotopic signature of TCs and how well do we understand that? And so proxy-based TC reconstructions assume that TC rainfall contributes significant anomalies in the annually integrated delta 18O of precipitation, and also that shifts in tropical cyclone seasonality or intensity don't alter basically the proxy fidelity or sensitivity. There are existing isotope-enabled simulations of TCs, but they tend to be very idealized and focused on fine-scale processes, and they have a limited regional scope. So what I've been doing is leveraging these high-resolution isotope-enabled CSM 1.3 simulations, which Betty mentioned yesterday, to kind of fill the gaps between paleotempestology records and then also idealized modeling studies. And so there are 60 years that I have found out, but I have 30 years of track data that I'm gonna talk through today. And I'm gonna use this data to kind of walk through three different approaches to understanding kind of how robust the isotopic composition of TCs is, or our understanding of that. And one is just validating ICSM 1.3, then two, trying to expand our understanding of that climatology, and then three, since this is a paleo session, identify regions that might be sensitive to variability in TC frequency that perhaps are not targeted right now. Okay, so just to walk through my methodology, so we have, through an algorithm, identified basically TC features from these ICSM simulations, and each TC is associated with 6 hourly snapshots or nodes. And so for each of these 6 hourly snapshots, I'm defining the TC radius, or I'm scanning a 1,000 kilometer area around that center point, and identifying where precipitation drops below 0.5 millimeters per hour. And now this is the tropical cyclone radius. And so everything within this circle is going to be like TC rain, or the TC associated field, and everything outside of that will be non-TC. And so using this radius, I'll also apply that to subset the isotope fields, which are weighted based on precipitation rate. And so repeat that for all the time steps. And computing a mean radial profile of both precipitation and then also these isotope fields, and then compositing that to get a mean radial profile for each storm, and then we'll be looking at basically spatiotemporal trends in that. Okay, so just to start with model validation, okay, so to give you some background, the isotopic composition of tropical cyclone rain is not uniform even within a single storm, and we know this from observations, but also these kind of ultra-high resolution studies, or modeling studies, where the delta D and the delta 18O of rain is most negative in rain bands in the eye wall, and then it kind of increases outwards away from the track center. And so just to ground us with precipitation, which we know is strongest in the center of TCs, the reason why this looks like just a filled circle instead of having some asymmetry is because this is a composite across all TCs that I didn't like orient. So I'm mixing in southern hemisphere TCs with northern hemisphere. So it's just a kind of more of a circle. But ICSM is reproducing these trends of precipitation intensity, and then looking at the delta 18O fields and the delta D fields across all global TCs, it also is showing these more negative values at the center that increase outwards. So this is really good. This is great. So at the base, the ICSM is reproducing kind of these observed trends in isotopic composition. And then, okay, and this just highlights what I said, that the isotopes are most negative in the center where precipitation is heaviest. Okay, and so then summing kind of all tropical cyclone associated points with non-tropical or all other points, and looking at the distribution of that, we can also see that values are more negative overall, or values of rainfall associated with TCs are more negative than values of rainfall associated just in normal precipitation. So this is good. ICSM seems to be reproducing these expected patterns. Okay, so next, expanding our understanding of kind of how this, I just showed you these patterns for TCs averaged globally, but let's break that down a little bit. Okay, so first question is just, does the isotopic composition vary spatiotemporally? And so these are various basins that roughly follow the IB tracks basins for where we have different kind of, or where there's different seasonality of tropical cyclone genesis. And so, yeah, that looks okay. So summing this all together is that the Western North Pacific and the Northern Indian basins, which are in pink and purple, seem to have the highest rainfall rates overall and also the lowest delta 18O and delta D of precipitation, whereas tropical cyclones that form in the Atlantic, both the northern and southern Atlantic, have lowest rainfall rates and then the highest isotope values. They also show those radial trends from lower in the center to higher kind of as you move away from the TC center, but the magnitude is of that inside TC, outside TC is bigger in the Pacific and the northern Indian basins. This could have to do with the seasonality of when cyclogenesis is occurring. I haven't analyzed this any further beyond just plotting basically these seasonal climatologies of TC genesis count, but that's maybe something to consider as how are these precipitation or the precipitation isotope values kind of correlating with background conditions that are occurring in JJA versus DJF or something else like that. But I don't know yet, so let me know if you think that's a good idea. Okay, so next, as I sort of alluded to in one of the earlier plots, those Western Pacific and the Northern Indian TCs have the highest rainfall rates, and they also have the lowest delta 18O values or delta P or delta D values. So natural question is, does the isotopic signature of TC rain also vary with storm intensity? Because more intense storms tend to be associated with more precipitation. And so plotted in the top is TC intensity based on the 10-meter wind speed. You can see there's the darkest red colors in the Western Pacific. And you can see that coming out a little bit in panel BB, which should be fancy, which is the distribution by basin. And so instead of breaking out by basin, though, what I've done here just for now is created these same radial profiles, but stratifying storms based on the terciles of the 10-meter wind speed. We're not going to be capturing the full range of tropical cyclone intensity, so 4 or 5 in this 25-kilometer simulation. So that's why I've just broken it up by like top 3 most intense storms and lowest 3 for now. But something I could do in the future is bias correct. But anyways, showing that the most intense storms do have higher rain rates and also more negative precipitation isotope values at their center. It's a little bit hard to see in this plot, so I'm also just going to plot distributions of now the precipitation and the isotope values only within the TC radius, which I don't have plotted here, but not, they're not all going out to 500 kilometers. Some might be 100 kilometers, some 250. And so just looking at the distribution of isotope values within the storm centers, you can see that those dark brown lines are shifted towards the negative values. Okay, so this is my least well thought out section. So yeah, I would love if anybody has kind of ways to improve this, but maybe let's just walk through this as a proof of concept for now. And the idea is, okay, how can we use this full, the full fields of ICSM of these model simulations to identify where you're going to have a high signal to noise in your annual delta 18O signal, which might be good regions to target for proxy-based studies. Right, okay. And so just looking across basins, so how strong is your difference between TC rainfall and non-TC rainfall? I'm just showing oxygen isotope values here. And you can see all the basins tend to have more negative values associated with TCs than non-TCs, but whether or not those distributions are like statistically significant or falling within or like well beyond the range of non-TCs varies by basin. Okay, and so then for these, what I wanted to understand is like, okay, even if TC rainfall is more negative than non-TC rainfall, what does that actually mean for the annually integrated delta 18O of precipitation? So to do this, I just looked at the top 10th percent, or basically the top 10th percentile and the bottom 10th percentile of TC frequency years. So high TC years are in blue and low TC years are in red. And then plotted the mean annual delta 18OP for these 2 years with the same colors. You can see even if there is a difference in TC counts between high and low years of 8 or more, this doesn't seem to be bearing out in any kind of meaningful differences in the annually integrated signal. Now, with the caveat that I'm looking at these really basin-wide, for these plots, these are those large basins, whereas most proxy studies are going to be integrating a much smaller domain. And so to think about that is we might want to look at where do TCs contribute significantly to mean annual rainfall. So this is just where does TC rainfall contribute a significant fraction of annual rainfall? And then also, where's the isotopic signature of TCs most distinct from non-TC rainfall? So that's going to be where you have those strongest red colors. So we might want to pick out smaller regions where you have a really high or a large difference between non-TC and TC rainfall, and also a significant contribution of mean annual rainfall to TCs. So I'm just going to show you now this analysis for Northwest Australia. Same as before. It looks okay. Like there is some more distinction in the Delta 18O or the integrated Delta 18O climatologies between high and low TC years. But interestingly, the lines diverge less during the tropical cyclone period. So still kind of teasing this apart, going to test different regions and trying to figure it out. But this is the direction that this analysis is going. So just to summarize these key takeaways is that ICSM 1.3 generally well captures these observed and modeled trends in the radial distribution of precipitation isotopes. We can then use the model to expand our understanding of how the isotopic composition of TCs varies over space and time and with intensity, potentially other factors. And then still looking into some regions that might be more sensitive to capture TC variability than others, but working through that. So thank you.
We have time for a quick question.
Hi, really great talk. This is maybe more of a general question, but is the more depleted O18 in the TC just because there's more rainfall, or is there a different convective process going on that's just fractionating it more?
That is a great question that I should have more insights to, but I don't right now. So I'm sorry, that's not helpful for you. So I don't know exactly why TC rainfall is more negative. You can assume it's sort of like an amount effect, maybe. But I've also seen studies looking at kind of these are like air observation campaigns, and they find that you can get variations in the isotopic composition of TC rain over its life cycle that spans the range of that region's annual climatology. So clearly there's different processes acting at different time and space scales within the TC. So stay tuned. Sorry.
Thank you. No. Yeah.
There's a question online for you.
Okay.
Can you quickly address it? Well, I'll show you that.
Okay.
And you can answer it online.
Okay.
Yeah, we'll save the question. Sorry, David. We will save your question for later, David. In the interest of time, let's move on to our next speaker, Chandler Morris.
Hi, I'm Chandler. I'm a PhD candidate at Brown University. I'm working in the Cobb Lab and with the Paleo Working Group here at NCAR. And I am working on a data model comparison comparing INSO-driven hydrological variability in the tropical Pacific Ocean via sea surface salinity and oxygen isotope observations. So just as some background and motivation, I have a paleoclimate, coral-based paleoclimate background, as I know maybe some people in the room here do too. Coral oxygen isotope ratio, or delta O18 records, are the primary basis of our understanding of INSO in the pre-industrial era, and therefore are how we understand how it changes through time on longer timescales. Coral delta O18 records, as you can see from this little figure I have here, are influenced or a function of both sea surface temperature and the oxygen isotope composition of the surrounding seawater. Thus, coral delta O18 records are indicators of both INSO-driven sea surface temperature variability as well as hydrological variability. However, in order to disentangle these two effects or these two records of variability, we need modern delta O18 of seawater observations to interpret our coral-based records and understand past hydrological changes. So seawater delta O18, I'll breeze through this since most of you know about isotopes, is reflective of regional hydrological circulation and moisture balance, and therefore co-varies very strongly with sea surface salinity. I'm showing that relationship here on the plot in the right, which shows the slope of seawater delta O18 and salinity across the tropical Pacific in both ICSM and observations. So you can see seawater delta O18 becomes more negative or depleted as salinity becomes less, so more fresh. But seawater delta 018 can also be affected by regional or localized ocean circulation and advection processes and incorporates that unique isotopic signature. So it's a little more complicated than a one-to-one comparison. Because of the contribution of delta 018 of seawater to paleoclimate reconstructions, and the recent advent of isotope-enabled models, which can resolve these fields, data assimilation efforts have been using isotope-enabled models, including the isotope-enabled community Earth system model, to integrate these records as well as modern observations to extend our understanding of INSO and hydroclimate change and reconstruct these timescales of variability, such as INSO and centennial variations and trends, through the past into the present and potentially into the future. However, there have not been detailed investigations or comparisons to understand how these scales of variability behave in isotope fields in ICSM, which is very important to understand and use these in a data assimilation context. So with that in mind, my goal is to use an observational network across the tropical Pacific to characterize hydrological variability on various timescales and evaluate ICSM performance, hoping to answer the questions of how accurately ICSM historical ensembles reproduce the tropical Pacific hydroclimate mean state through seawater delta 018 and salinity, and where structural model biases emerge relative to our observations. And then further, how well does ICSM capture hydrological variability that's documented in our network, from the seasonal cycle to INSO-driven hydrological variability? So I'm just showing you here our observational network across the tropical Pacific. These are paired delta 018 of seawater and salinity observations, which provide pan-Pacific coverage of mean state and also of the recent 2015 to 16 and 2023 to 2024 El Nino cycles, or El Nino events. It's worth noting that these monitoring efforts are continuing through the upcoming El Nino event, so they'll provide coverage of that as well. So using these records or observational time series, modern time series, just so everyone knows, that span longer than a year, I'm comparing mean state estimates. I'm showing the ICSM last millennium ensemble mean from the past 50 years, so 1950 to 2005, across those 4 members. So we can see across both our observations and in ICSM, we're simulating a wetter or more depleted delta 018 seawater and fresher salinity values in the Western Pacific warm pool. And we're seeing drier conditions in the eastern to central tropical Pacific, where we have higher salinity values and higher delta 018 seawater values. So ICSM is capturing the mean spatial structures of these fields with correlations in delta 018 seawater, spatial correlations of 0.5, and in salinity of 0.6. However, when we zoom in site by site, we do see evidence of a modest freshening bias across the tropical Pacific. Obviously, there are exceptions to that finding, and there are a lot of nuances in our observational network that I can talk about later. But we are seeing evidence in delta 018 seawater of a slight freshening. Here I'm showing our observations on the left with air attached, and the ensemble mean to the right, where the air bars are showing the distribution of mean estimates given the sample size of our observational time series on the left. We see further support for this in salinity fields of a potential freshening bias in ICSM, and our observations are largely agreeing with previously published observational estimates from Argo and Tokatau time series and reanalysis salinity data as well from the area. When we look at precipitation data, so I'm showing in situ precipitation amount and delta 018 of precipitation, we see a possible atmospheric-driven freshening bias. As across all sites, we're seeing a more depleted delta 018 of precipitation in ICSM as compared to the observations, which would suggest a more enhanced amount of rainout at the sites in ICSM than in our observations.
So moving on to see how we see variability across the mean state in the seasonal cycle. Right now I'm showing you Galapagos in the Eastern Pacific cold tongue. Galapagos, the seasonal cycle is largely driven by the equatorial undercurrent, where in the spring months, a stronger upwelling effect brings more positive delta 18 seawater values and more high salinity values here that we're seeing that spike. This area is very cool and dry, so we don't see much of a wet, dry effect here. We see compared to ICSM, which I'm showing all of the members here, that it's not capturing the amplitude or the phase of seasonal variability at Galapagos. In fact, it underestimates seasonal variability or the amplitude of the seasonal cycle in delta 18 seawater by approximately 70% and in salinity by 60%. Offshore salinity observations, which I'm showing again here in this straight pink line, support this dampening as well, further supported by a reanalysis product that I'm showing here, ORS5. We see a similar effect, especially in delta 18 of seawater at Christmas Island in the central tropical Pacific, which is a similar climate regime where it's very dry most of the year. And we also brought in a finer scale or a higher resolution regional ocean model, ISOROMS, published by Stevenson et al. In 2018, which better captures the amplitude of this seasonal cycle in delta 18 of seawater, which implicates a potential role of subgrid scale processes that are not resolved by ICSM in this observed delta 18 seawater variability. However, when we look at Palau in the Western Pacific warm pool, which has a seasonal cycle primarily driven by increases in rain, like a wet and dry season, we see that ICSM is better capturing this variability in delta 18 seawater and salinity. Furthermore, when we look at precipitation data, we see that ICSM is capturing the amplitude, especially in delta 18 of precipitation. So both of these results in combination suggest that we possibly are seeing an ocean dampening in ICSM of this variability rather than an atmospheric response. So in order to understand INSO-driven hydrological variability, I focused on the 2015 to 2016 El Nino event, where we have coverage at Palau, Christmas Island, and Galapagos. So in order to compare apples to apples as close as possible, I built a composite of analog events in ICSM by comparing the amplitude and spatial expression of sea surface temperature anomalies using common spatial indices. So here I'm showing on the left that composite of sea surface temperature and precipitation on the bottom, as well as the observed anomalies through the 2015-16 event. So when we move to these hydrological variables of delta 18 seawater and salinity, we see that at Palau, as we would expect just from a climatic dynamical standpoint, we see more positive delta 18 seawater and salinity anomalies, indicating a drier climate during this El Nino peak. However, this sign and the amplitude of change is not replicated by ICSM. We see a similar dampening at Christmas and Galapagos, where we see a freshening of delta 18 seawater and salinity, this anomaly going negative space, which is up on this y-axis. And again, the sign and amplitude is not replicated by ICSM here. This is especially important from a paleoclimate view using coral-based records, because this is exactly what coral-based records are recording when we think about hydrological INSO-driven variability. However, once again, when we look at the atmospheric lens or precipitation amount in delta 18 of precipitation, we actually see that the amplitude is reasonably captured by ICSM. So again, indicating that there might be a dampening happening in the ocean component of ICSM. So just as some broad takeaways, ICSM is capturing the mean state spatial structures of hydroclimate across the tropical Pacific. However, it does demonstrate a dampened seasonal and INSO-driven variability in seawater delta 18 and salinity, perhaps due to a coarser resolution or some sort of dampening of ocean dynamics there. Future work will extend this comparison to La Nina events and the 2023 to 2024 ENSO cycle, and possibly the upcoming El Nino event. Furthermore, this comparison can be applied to future versions of ICSM. So thank you, and I'm happy to take any questions if there's time.
We do have time for questions. 2 minutes. I'll ask a quick question. Well, maybe, I don't know how quick it is, which is when, it seems that there is some dampening happening in the ocean with respect to seasonal and the expression of ENSO events in the seawater isotopes. Have you considered bringing in more observations of the current speed or more of the kind of physical state of the ocean?
Yeah, so at some of these sites, we do have like physical oceanographic data sets, like current speed and velocity and everything. So that would be interesting to bring in. A lot of these sites are more remote, so there's not, like, it's hard to come by even like CTD salinity data. So that would be more of like a zooming in on one particular site to look at. But I do think that would be an obvious next step to look at whether it's a vertical resolution problem, so there's some dampening happening because of the depth of the surface layer in ICSM, or if there's actually something with the advection and mixing happening in the horizontal resolution. But yeah, there's also more salinity data sets to bring in, but for this purpose, I was just keeping it to the same 1x1 degree grid box as ICSM, or comparing. Oh.
Do we have any additional questions for Chandler?
Yeah, similar question. Great talk. Have you looked at any other models to see if they have like a similar issue in the ocean?
I haven't. I know there's like a few other isotope-enabled models, including like a recently published one that would be interesting to look at. I did like the ISO-ROMs, so the isotope-enabled regional ocean model I've been bringing in, but I think future work would definitely be to get whatever isotope-enabled model we have and compare it. But yeah, thank you so much.
Okay, we'll move on to our last but not least talk in the session. Charlie.
Thank you. Thanks everyone for sticking it out to the bitter end. I'm Charlie. I'm a postdoc at the University of Connecticut, and I'd like to talk about some atmosphere-only CAM6 simulations we've been working on. So, maybe. It's kind of nice to go last in this session because I don't need to belabor this point, but you've seen a lot of examples of why climate scientists and paleoclimate scientists really like water isotopes. They track a bunch of different things in the climate system across scales. We've seen stuff from orbital time scales all the way down to tropical cyclones. Across spatial scales, they track these big things like ENSO, they track these little things like storms. And so we're all very interested in how we can use isotopes in modeling and proxy reconstructions more. But the fact that they're so versatile is also kind of a double-edged sword, because if they track every single step of the hydroclimate, every phase change of water, it can be a little hard to know for sure, if you have an isotope record, what signal is that recording exactly. We've also seen that water isotopes are useful because they show up in a bunch of different proxy types. Speleothems, paleotempestologists might find them in trees. And so it can be difficult if you're creating a proxy reconstruction based on water isotopes to know for sure what signal from the climate that record is recording, and this is where isotope-enabled simulations can come in and really help. So I'm going to go through this kind of quickly because I think we have a hard out at 4, and I think a lot of people here are very familiar with isotope records, but I think it's worth going over some of the different large-scale signals isotope records are interpreted as, because it'll help us understand the things we look for in the experiments I'm going to show. So the first like original Willie Dansgaard 1964 isotope signal that he thought about was temperature. So he noticed that when he just collected rainwater from his, I think, porch in Copenhagen or something, that the isotopic composition of that water changed depending on the condensation temperature of the rainfall. And so, as Maya said, this relationship might hold more in high latitudes like Copenhagen than it does in the tropics, but it's still an important thing to consider. And then obviously, if we're looking at stable isotopes in precipitation, delta 18O precipitation, we assume it'll track hydroclimate in some meaningful way. But even that is subject to some discussion about what exactly about the hydroclimate the stable isotopes track. So, I also want to discuss what about hydroclimate, what about large-scale changes in rainfall might be tracked by isotope records. So, the other part of the Willie Dansgaard, now he's like looking down or across at a convective system, was there's an amount effect, which was Anson also talked about. It's basically just like if it rains a lot, you get a different isotopic signal than if it only rains a little. This has been kind of refined since the 1960s, but it's still an explanation for isotope signals that you will see invoked today. Some more recent work based on observations in the tropics has indicated that rather than purely the amount of rain, if you have stable isotopes in precipitation, what it's actually tracking is the type of rain you're seeing, so that there's a difference between sort of large scale or stratiform rainfall, which doesn't involve a lot of vertical motion in the upper atmosphere. That is a different isotopic signal than convective rainfall, where there's a lot of motion, which has a fractionation signal. And so you end up saying that our isotope records are tracking the percent or fraction of stratiform versus convective rain you see. And then somewhat more recently, someone looked at some different observations from the tropics and concluded that the stratiform fraction theory was actually not true. It was just sort of a masked version of a different effect, which was convective strength. So basically, if you have really strong convective systems that go very high up into the atmosphere, they can get as high as the stratiform systems. And so it sort of occludes that signal. And you end up with your record mostly tracking convective strength. And for our purposes, we're going to use outgoing long-wave radiation as a stand-in for convective strength, which is just based on cloud top temperature. So, given that our isotope records and even the isotope signals we see in models could record a lot of different signals over large scales, it's useful to stop and consider if we can use models to answer the question of which of these signals are most imprinting on isotope records. So for this study, we're focusing on the North Pacific. There's two reasons for this. One is that there's a proxy record being developed that sort of spans the western coast of the United States from leaf wax records that goes far back in time, which allows us to create a gradient of delta 18O of precipitation. And then the other reason we're interested in this is there's a lot of community interest in the problem that models are having getting the equator to high latitude temperature gradient right in the Pacific. So we're interested in ways we can use isotope models to constrain that, whether it has to be from cloud feedbacks or from sea surface temperature patterns and there's effects. But for the rest of this talk, I'm going to be just talking about the gradient of delta 18O of precipitation in the North Pacific. And so we'd like to focus on two questions. One is, does that gradient change in different climate states? Because that can give us useful information about things like sea surface temperature and cloud feedbacks in those climate states. And then the second one is, if it does change between climate states, is that the result of dynamic changes in the climate, or is it that the isotopes are recording a different signal? So to answer this question, we ran some isotope-enabled CAM6 simulations, pretty coarse resolution. We used as our boundary condition just the standard CSM, PI, seawater isotopes. We did a sensitivity test where we tried like setting the whole isotope field to 0 on the sea surface, like making the whole ocean VSMO basically. And it didn't have a very big difference, so we continued using PI seawater isotopes for our experiments. And the two climates we were interested in are the last glacial maximum and the Pliocene, which you've heard about both in previous talks in this session. But briefly, the last glacial maximum was like 21,000 years ago. It was cold. And then the Pliocene was 3 million years ago. It was relatively warm, and we had CO2 levels analogous to what we have today. And we ran 4 experiments, and I want to be very precise that these are not Pliocene and last glacial maximum experiments as much as they are sort of Pliocene and last glacial maximum-like experiments, because the only things we were changing from the pre-industrial were sea surface temperature patterns. So we ran for each time period a uniform warming and a uniform cooling, where we just added 4 degrees or subtracted 4 degrees from the sea surface temperature. And then we did 2 pattern effect simulations where we perturbed the sea surface temperature with sea surface temperature patterns from the Pliocene DA for the Pliocene, and then the LGMR, which Maya talked about for the LGM. So again, we're focusing on the North Pacific and the gradient of isotopes in this region. So the figures I'm showing will be zonally averaged from this box, and here are the lat long coordinates if you like. We've done some tests with different boxes. They're interesting, but you know. Okay, so what I'm showing here are just the gradients of the delta 18O precipitation in the North Pacific. On the left is the pre-industrial simulation, and the 2 Pliocene-like, the plus 4K and the Plio-DA pattern warming experiment. Then on the right, we're showing the last glacial maximum-like simulations. And so you can see both have just like generally from the equator, which is at the left, up to 50 degrees north on the right, a general downward trend, which is what we expect from Rayleigh distillation and other kind of temperature gradients from the equator to the high latitudes. But there are features of them that are different and interesting that we want to discuss. So the first is there's this trough that appears sort of between 10 and 20 degrees north in the Pliocene experiments that is much shallower in the last glacial maximum experiments. This could be from the ITCZ. It's kind of how we've been interpreting it so far. And then the other interesting feature that we want to explain is this kind of peak around 30 degrees followed by a decline, which could be due to Hadley, the descending branch of the Hadley cell. So I want to say it very much could be true that these are different in the last glacial maximum and Pliocene experiments due to dynamical differences in the climate. So it could be that the ITCZ is shifted, it could be that large-scale atmospheric circulation is changed, and that explains sort of the change in what we think is the Hadley cell descending's location. For the purposes of this talk, I'm going to just discuss the signals that they record rather than the potential dynamical differences to see if the differences we see could be just due to changes in that signal. So as a reminder, here are the 4 kind of large-scale signals we discussed. I'm just going to show you now the same thing, the gradient of delta 18O on the left, and then the same area, the same gradient from the equator to the high latitudes for each variable we're interested in on the right. So for the first, we have temperature. Again, temperature follows this kind of broad decline, but it doesn't explain the trough or peak we see. So for the rest of this talk, we're kind of ruling out temperature for both of these experiments because there's just kind of that broad decline. There are interesting differences in each of them, but I don't think we have time to get into them. So ruling out temperature, we're going to look at the other 3 potential types of hydroclimate signals that they might record. So the first is just the amount of convective precipitation you see, and you can notice, it's kind of hard to do this wiggle matching, but the troughs in the delta 18O do correspond to these sort of peaks in convective precipitation amount, and then where they go down or peak again, there's like a corresponding trough around 30 degrees. They're not lined up exactly, and the Plio-DA has this like weird spike around 40 degrees in its precipitation amount that doesn't show up in the isotope record. But it does seem like there's maybe an amount effect captured in isotopes for the Pliocene-like simulations. For the LGM-like simulations, you see kind of a very similar big peak, but because the troughs aren't as present in the delta 18O gradient, we think that might mean that like precipitation amount is not the strong driver of the gradient we see for the last glacial maximum. We do the same thing for convective percent. You don't really see the troughs or peaks appear. Sorry, I know we have to get out of here soon. So we think maybe convective percent, I'm good. Okay, thanks. There's not, the shape of the figure on the left is what we were trying to replicate in the figures on the right, and the convective percent, which is kind of the inverse of the stratiform fraction, does not capture that. which makes us think that it is not as strong a driver of the isotope signals for this climate. And then in the LGM, they actually look pretty similar. The LGMR is doing something kind of weird, but we don't have to do a ton of wiggle matching because I'm going to show actual linear regressions in a second. And then lastly, we check convective strength. And I think you see, similar features emerging, but it's kind of what you would expect if it is the intertropical convergence zone. Like these areas of convection do show up, but they actually don't seem to have moved as much. If you look on the right, they're all still around like 10 degrees or so, whereas in the Delta 18O, there's sort of like a northward migration that happens in the Delta 18O record. And then, again, for the last glacial maximum, this is the last one, I promise, you see this deep trough that doesn't exist in the Delta 18O record, so it seems that that's not imprinting on the isotopes as strongly. So there is some reason to believe that in warm climates and cold climates, there are different signals being recorded by Delta 18O of precipitation. Again, that was just wiggle matching. We can also do like linear regression, which is slightly more sophisticated. And so here what I'm showing is just linear regression for the uniform warming and cooling effects, so the plus 4K on the top and the minus 4K on the bottom. And you can see that convective fraction has strong predictive skill for each climate, but convective strength, which is measured by OLR, which is on the far right, has maybe stronger predictive skill for the last glacial maximum than for the Pliocene, and then convective amount doesn't do a very good job. The scatter plot doesn't look very good. And we can do the same thing for the Plio DA and LGMR simulations. We see that like convective fraction has by far the best predictive skill for the Plio DA pattern effect, and then both convective fraction and convective strength seem to have a lot of predictive skill for the last glacial maximum resolution. So now is where I'm like kind of going off the rails. We also did a multivariate linear regression, but I need to like caveat this a lot. So if you want to compare like the coefficients in a multivariate linear regression, you have to standardize all your predictors, which we did, but you also need your predictors to be pretty independent. And I think like convective strength, convective amount, and convective fraction are all probably pretty collinears, not one-to-one, but they are probably related to each other in pretty significant ways. We do intend to get around this by using some hierarchical models to do regression and maybe some neural network type things, but for the time being, I do think it is interesting to say that for the warmer experiments, convective fraction has more predictive skill, and it has almost none for the LGM-like climates, where convective strength has by far the strongest relationship with the isotope signal. So I'm just going to leave my conclusions up here and say, I think when we consider isotope records, we need to consider both dynamical changes that could lead to those, but also whether those dynamical changes are leading to changes in the signal that imprints on isotopes. And isotope-enabled experiments are a great way to do that. And I can't wait to use ICSM 3. Thanks. Yeah, I'm done.
I think in the interest of time, please approach Charlie after for questions. Thank you so much. Let's give another round of applause to all the speakers. Please, attend the wrap-up discussion for the workshop and then the happy hour at Pattern Break Brewery at 5:15. Thank you.